All right, Algebra Squad part 2 for this worksheet. So you know what? I freaking was made aware in 5th period that Desmos was not popping up. So it took until 5th period for somebody to mention that Desmos was not popping up while I was talking about all of this. So what the heck were you guys doing before 5th period that you guys didn't tell me that? Mr. C, it sounds like you're talking crazy because you're talking about some stuff, but we're not seeing it. So I think I figured it out. So let's go ahead and see. The first thing I need you guys to do is to have obviously this worksheet in front of you, because I do want to just take about 1 or 2 or 3 of these graphs and show you what you can do in Desmos to make it all make sense to you. All right, not just do the work and go, all right, I'm just doing it because Carreño's saying it to do it. So I want you to focus on these numbers right here. All right, so I'm gonna go to Desmos in a second, and so we can. All right, we should be in Desmos now. We're in Desmos, and what I need to do is go ahead and write the equation. The equation is very simple. The very same one that was given to us, negative 2x, minus 3. And I'm using the keyboard to do this. So if you're wondering what the heck I'm doing, you're just using the keyboard. So negative 2x minus 3 equals y. That is the original equation that was given to us. And if you're also probably, maybe not, you're probably wondering if I turned the equation around. I don't know if you remember from yesterday, I had turned the equation around so we can have y on the other side, which my brain always wants to do that. You don't have to, but just to show you that it's the same thing. Doesn't really matter. All right, so what I was telling you yesterday was, okay, let me get something out of the way. Okay, there we go. A line is made up of infinite amount of points. So notice that I can drag this cursor here and it's going to show you all the infinite amount of points. And yesterday I used the word billions and trillions because yes, I can keep zooming out. I can keep zooming out forever and we get insane amount of numbers. So right now I'm at 52,000 in my X number and 104,000 in the Y value. So imagine, think of all these numbers, and if the more I zoom in, so that's zooming out, I can actually zoom in a lot more. Now I lost track of where it's at. And you can understand that we can go into ugly, tiny, insane decimals, all right? The word infinity actually is a thing here. But like I said yesterday, we only want to put points that are pretty much simple for us, just so we can get an idea of the of what the line looks like. As soon as we get 2 points, because remember, look, you only need 2 points to make a line. You make 2 points, you make a straight line, and that's it. So if you look at your X and Y chart, your table of values, you could see where I got the negative 1.5 from. Yesterday, I said, oh, I know you saw the negative 1.5 because I showed you this on Desmos before we actually graphed it. So I was like, all right, let's go ahead and use 1.5, negative 1.5, so we can see that we actually get 0 once we solve it. So that is one of our numbers. Another number that we chose as our input was X. As our X input was 0. So when X is 0, you could see here that the Y is negative 3. So the equation, this right here is it's kind of like a machine. It's a machine that you input an X value and then you solve it and you get a Y of an output. So you can see that that is why it's infinite, because you can put in every single number, any number in the world, and you're going to obviously solve it and get something new. If we look at 1, where X is 1, which would be this line right here, and we go down this line to see what happens, it's you can see that it's paired with negative 5. I'm trying to get it like exactly to it, but I don't have there it is. 1 comma negative 5. All right. And if I were to go to negative 6, which negative 6 is right here, and go up, you could see that it's paired with, what is that? Come on. Oh my gosh. All right. Well, we could see that it's this line right here, which would be 9. And that is exactly what we have in the table of values. I give up. All right, cool. So the next thing that I wanted to show you was the example number 3, when I was talking about when Y equals a number, and example number 4, when X equals a number. So when I have Y equals, and I use the example of 5, when Y equals 5, notice what happens when I drag and I look at all the points where Y equals 5. These are where my 5s never change, where my Y numbers never change, right? My X changes because I'm moving left to right, but I'm never moving up and down. So my 5 doesn't change. And this will change if I put another number. Y equals negative 4. I got to zoom out really quick to find that line. -1, -2, -3, -4. Here it is. y equals -4. This is the line because your y of -4 will never change. So it creates horizontal lines. Then we have the idea of x equals any number. What number do we want to put here? It doesn't matter. Let's put 12.35. X equals 12.35. Where is that at? Oh, I have to zoom out because I have to go where my X number, right here, that's 10, 11, 12. And look at that, 1235. Everywhere is 1235. So once again, we don't have to just think about pretty whole numbers. This works with any number in the world. And let's just make it 12. And now it's a pretty number. And there you have it. Don't forget, we zoom out, this line goes forever, and it's always at where X is 12. All right. So that's pretty much the idea of what Desmos can do for us to help us understand how to graph this and make sure that our line looks correct. Okay. So let's jump back to bada bing, bada boom, the worksheet. All right. Let's go ahead and check our work for this check problem. I'm like 90,000% sure that 100% of you did not do this. So let's go ahead and see if maybe you did, but let's see if you did it right. So we have this problem here, but we could see that the y value is not isolated. So step number one, maybe you were like, what do we do? Well, you need to make sure it's isolated first. I said that the very first problem that we did, we want y to be isolated on one side. That way we can call it f of x and just move on from there. Since I'm taking 4 by division, I'm going to kind of do it separately to the 12 and to the 36, just so I can understand what's happening to both of them individually. A -12 divided by a +4 gives me a -3. Fraction is gone. 36 divided by 4. So what number do I multiply 4 by to get 36? That would be the number 9. All right. Let me move something out of the screen here. Okay. So this is pretty much the equation I'm working with. Now I can go, okay, what table of value numbers, what x's and y's am I going to be using? I always want to start with, so remember that this is now f of x equals -3x plus 9, and I'm inputting numbers for the x in there. Always start with 0 just to get an idea of what's happening at 0. Okay, so 0 times -3 will make the 3 go away, the -3 go away, so I'll be left at 9. And lucky for us, we do have space here to get to 9. So 0, and then it'll take us to 9, which is between, because remember, these are counting by 2. So it's going to be between 8 and 10. 10 is a top line. Let's go to 1. Let's see what's happening, where the line is at, located at 1. So f of 1 equals -3 times 1, which is -3, plus 9. -3 times 1, it stays at -3 plus 9. So it's the same thing as saying 9 minus 3. 9 take away 3, that puts us at 6. Okay, puts us at 6. So at 1, we are now at 6. Okay, let's go with, I think you can have the idea, or you can sense the idea that if I were to put negative numbers, I could see that this line goes downward from left to right, it goes downward. So if I put like a negative number, like say -2, I might be out of my graph. I'm just going to do it just so I could see that I'm not going to be able to, most likely not see the point in the graph with how small this graph is. -3 times -2, 3 times 2 is 6. A negative times a negative is a positive. So it's +6 plus 9. That gives me 15. So I'm out of the graph. I'm not going to be using that. I will not be using this point to show it. Even though it is on the graph, we can go to Desmos and find that point on the graph. We're not going to use it. So let's just keep going with positive numbers. I know that I won't go to the left because I won't see the line that way. So let me just get some other numbers here. Let's go with what, 3, f of 3 maybe? Oh, let's go with 4. Let's go with 4. -3 times 4 plus 9. -3 times 4, that gives me -12. -12 plus 9, 9, 10, 11, 12. So that's going to give me -3. So at 4, I will be at -3. So at 4, I will be at -2, 3, right here. Okay. Cool. I think that's going to be good enough. Let's create our little line. So whenever you guys are doing your classwork or your homework, whatever the case may be here, always you're allowed to jump on decimals. Nobody's checking up on you, to just make sure that these points are on decimals and they do align, that your line looks exactly like that. But for now, we're going to go ahead and move on to this question right here. We're going to do it together. And to see how this is used with a real world scenario. Angelina works as a nurse in an emergency department. Some patients who are dehydrated require rapid rehydration with intravenous saline. As you can see, I've never said that word before. Suppose that the function 50x plus 3y equals 1500, and then it says it represents the amount of saline in millimeters left in the bag y after x minutes. So I don't know if you guys have seen it in movies or maybe gone to the doctors before. That's the little liquid bag that hangs. It's there's a rolly thing, right? And then the saline, this little liquid, goes into the person, right, into their body, which if it's the arm, whatever. So what's happening here is that this liquid is being obviously pumped into you, so it's going down. That's what's happening, right? So the equation will tell you how much saline is left in the bag after X minutes. So the more minutes that go by, the less liquid is in this bag, right? That's pretty much it. So right now we're going to be graphing the amount of saline left in the bag as a function of time. Whoa, that's a lot of words here. So we're going to make a quick sketch here. The very first thing I want to do is kind of ask myself, what is this going to look like? How am I going to be graphing this? Because we learned two ways of going about graphing in this worksheet. Number one was creating the table of values, and then just putting inputs and then getting outputs out, which is this right here. And number two, the second way that we did it was, oh my God, you know what? I just shot myself in the foot. This question is doing it with X and Y intercepts. So yeah, we're gonna have to talk about that in a second. That was the second way. So the first way was exactly how I did it here. And the second way was finding your X and your Y intercepts, putting them, and then just creating a line right through them. Okay. Well, fun fact, I found my y-intercept, which was right here. So let's see. This equation right here seems very hefty with numbers. If you ask me, making less points is a lot faster, right? So if we can just find the X and Y intercept, if we can find the X and Y intercept, it'll be a lot faster because we just find 2 points, draw them, and we're done, right? Hopefully you understand why I drew my coordinate plane like this and not all 4 quadrants, right? Because we're not going to utilize, if this is time, because time is passing, remember that time is X in minutes, and Y is millimeters left in the bag. So saline in bag, and it's in milliliters. Okay, so we're not going to be using the negative part of time. There's no negative amount of time, and we don't go down in the Y's because we don't have negative saline. If that runs out, the least you can have is 0. That's it. Okay, so I think finding the intercepts would be the easiest way from this one. Obviously, look what it says here, use the intercepts, but you do have the ability to choose whatever you want if this was not given to you. All right, so let's go ahead and do it. To find the y-intercept, I don't know why I started with this one, it doesn't matter. To find the y-intercept, I will make my x 0. So here it is, 50 times 0 plus 3y equals 1,500, 1,500. What happens here? That goes away. And now I have 3y equals 1,500. What happens next? I have the 3 taken to the other side by division. Cancel, cancel. To get y is equal to 1500 divided by 3, 500. So this right here is our y-intercept. Our x-intercept is pretty much the same idea, x-intercept, where our y value is 0. We will put a 0 for the y value, solve it. 50x plus 3y equals 1500. All right, that's going to give us 50x equals, obviously that goes away as we mentioned before, 1500, divide both sides by 50, cancel, cancel. That's the same thing as saying 150 divided by 50, by 5, we get 30. Cool. All right, x-intercept becomes this. So x is time, y is the amount of liquid in the bag. So this means that I have a point right here at x is 30. So I can label this however I want. And you have to remember that the saline starts at, the bag is, I guess we can consider it full, or the most liquid that it has. It starts with the most amount of liquid and then it starts going down. So our point, our y-intercept will be up, and then the line is going to take us down because the saline is going to go down as time passes. So you need to understand that the line will go like that. So I can now start to understand that I'm okay by putting 30 all the way over here. So if we count maybe by 5s, so I need 6 lines. 1, 2, 3, 4, 5, 6. It gives me a nice separation of space here. So 5, 10, 15. What did I say? Yeah, 20, 25, 30. So there it is, an x-intercept at x equals 30. All right, what do I have here? 500. Very simple. What do I what can I break these numbers by? Equal numbers, so I can get to 500. I hope you guys said maybe count by hundreds, and that's it. Keeping it stupid, simple, easy. So 1, 2, 3, 4, 5. 500, 400, 300, 200, 100. My y-intercept is located at 500. And that's it. We are done. I am going to now create this here. And this is how the saline is going to be every single minute. After 5 minutes, it'll be roughly this much. It'll be in the 450s. Okay. I'm just taking like a random guess. So just for a little entertainment, let's go ahead and jump back to Bitty Bitty Bam Bam to Desmos. Where my Desmo at? Right here. All right, so we're jumping back to Desmos, and let's look at the equation 50x, and I'm just going to type it the same exact way as I saw it at the beginning, just so I see if I made any mistakes, maybe doing the math by dividing by 4 at the beginning, right? Okay, so here is 50x. Let me just look at it again. 50x plus 3y equals 1500. I highly encourage you to maybe have an open tab and as well create your own. So let's start with our x-intercept. There it is. Now remember that this line looks a lot more steep, because we're pretty much 500 is a very large number. And right now we're counting by each thick line right here is counting by 20s. We counted by hundreds. So here it is. Here is our y-intercept, 0, 500. So this is the line that we recreated. It looks a little bit more steep than the one that we created because ours is a little bit more zoomed in, nicer to look at. This would be a little bit more annoying. It's like an eyesore to look at, a little bit more complicated. And let's see if I can find Let's see if I can find. Oh no, it's gonna be a pain in the behindy. Yeah, let's do it. I'm gonna try to do it right now. I'm gonna see if I can find where my X was 5, right? I said X was 5. It'll be around the 450s. Let's see. No, it's not in the 450. It's not in the 450s. Just I'm gonna leave it like that. About 415-ish. That's close enough. So as you can see, it was just like a ghetto estimation. All right, cool. We are done. Peace out. Do not turn this in until I ask for it. See you.